In this video, we'd like to derive a formula for what we call the binomial series. So the binomial series is the series representation centered at x0 equals 0 of a function of the form 1 plus x to the power k, where k here is any real number, right? So any real number k. And we want to try to find a power series representation for this, like I said, centered at the origin. So here's our goal. We've got this function, this power series function t of x, which is just a very simple power series. It's got these coefficients c sub n times x to the power n. So our t of x function looks like c0 plus c1x plus c2x squared plus c3x cubed plus c4 x to the fourth, etc. Right? And so this is a formula for just a generic power series here. So we want this power series, like I said, to equal this function. So what do we have to do? This is very similar to what we did when we derived the formula for the Taylor series, where we had to work out a proper formula for these coefficients, right? Can we find a formula for these coefficients? And what we can do is we can just take some derivatives of this function, and we can write down, we can plug in our center point to both sides, and we can write down a table basically of coefficients. And then we'll come up with a shorthand way to represent all this. So here's what we're going to do. Like I said, we're going to take derivatives. So let's start by making this giant table where, let's say, n is equal to 0. Our nth derivative of our function, if we haven't taken any derivatives, then our function is just 1 plus x to the power k. Then we need a formula for the fn applied at 0. And so this is just 1, right? And then finally, a formula for our t sub n, so our nth derivative of our polynomial function applied at 0. So I just erased that, but so t nth derivative applied at 0, which in this case, this is just going to be the formula, the coefficient c0. All right, so there we go. Now we got to go through and let n increase, right? So we take a derivative here. When n is 1, we take one derivative. Well, what happens? This is a chain rule, right? K comes down. We're left with k times 1 plus x to the k minus 1. We plug in 0 for x. We have 1 to any power is 1, right? So this is just k. And so this term, by the way, is c1. c1 times 1. So there's our c1. Then we go to the next term, right? So the next term is 2. When n is 2, we take another derivative, right? We get k times k minus 1, 1 plus x to the k minus 2. When we plug in 0 for x, we get k times k minus 1. We're starting to see how this works, right? But over here, what do we get? Over here, we get 2c2. All right, and at this point, so on the previous two, we were able to just say, all right, c0 is 1, c1 is k, right? But now we can't just do that, right? And so we have to be very careful at this point. And we see we should have another column for our table, our c sub n, and we should solve for this, right? And what do we find? We find that, all right, here, if we solve this for c sub 2, then we end up with k times k minus 1 over 2, right? So there's our c sub 2. Here we had c0 just equals 1. c1 is just equal to k. Let's go at least one more step. Take another derivative, right? What's going to happen? K times k minus 1 times k minus 2. All right, times 1 plus x to the k minus 3. Plug in, we see what's happening, right? This is just picking out these coefficients right here. And so this is k times k minus 1 times k minus 2. Over here, though, look what we have. 3 times 2 times 1. This is going to be 3 factorial, right? It's times c3, just like we got when we did the Taylor series. So this is really 2 factorial, 1 factorial, 0 factorial, right? And we're starting to see how this is coming together. When we write down the coefficient, we need these terms divided by that factorial. So the c3 coefficient is going to be k times k minus 1 times k minus 2 over 3 factorial. All right, well, we can probably guess now what c4 is going to be. So if we follow this process, right, c4, the next one's going to do what? It's going to multiply by the next, subtract one more, right, and multiply that, increase the factorial downstairs. So k times k minus 1 times k minus 2 times k minus 3, one more, right? All divided by 4 factorial. And what we really need to do then is we need to figure out a formula for this, right, in terms of n. So notice that this is our n, which matches this and does not match this, right? It's one off of this, but it's very close. And so we deduce that the coefficient, c sub n, for the binomial series, this is going to be called, the nth coefficient is given by k times k minus 1 times k minus 2, all the way down to k minus n plus 1, right? It's a little, so this is k minus parentheses n minus 1, 3, right? So, and then it's all divided by n factorial. And so this tells us then that our binomial series, this is like the Maclaurin series for this function, right? It's not just like it, it is. The Maclaurin series for this function is equal to this sum, n goes from 0 to infinity, of this product, k times k minus 1 times k minus 2, all the way down to k minus n plus 1, all over n factorial times x to the power n. Okay, and this, by the way, you should do this. So here's an implicit exercise, but I'm making it explicit, okay? So implicit, no longer. Exercise. You should be able to show that the radius of convergence of this power series is 1, all right? And then it should be not too hard to check the endpoints, and so this binomial series works only for x between -1 and 1. And you can show that, okay? Now, before we sign off, I'm sure you're thinking this is there's nothing necessarily wrong with this, but this is a little bit messy, right? This is a little bit messy. And so we have notation for this. So this is called a combination in other areas of math. And we can write down, if k is a positive integer, it's called a combination. But we can write this down for any value of k. And so what we can write down is this. We write k, choose n, looks almost like a fraction. This notation right here looks kind of like a fraction in parentheses, but there's no fraction, right? So it's just k. We read this as k, choose n. All right, it's really just a binomial coefficient, because when I say this choose, I'm thinking of k as a positive integer. Yeah, it doesn't always have to be, okay? It can be any real number, but what it equals is exactly this number right here, so this ratio. So k times k minus 1 times k minus 2, all the way up to k minus n plus 1, all over n factorial. All right, and so in this notation, we get to write our binomial series in much more succinct, nice form. So the sum 1 plus x to the power k is the function 1 plus x to the power k is equal to the sum. N goes from 0 to infinity. K, choose n in my notation, x to the n. And that's it. There's the binomial series.